Welcome to this explainer masterclass, everyone. Today, we're going to break down the optics of direct and indirect ophthalmoscopy. Now, my goal here isn't just to give you a bunch of quick facts to cram and forget. No, we're building long-term clinical mastery, stuff you'll use every single day on the wards. And yeah, stuff that's going to save you on the boards. We really want to completely understand the physics and the clinical application behind what we're actually seeing when we look into a patient's eye. So let's get focused, right? Let's build a solid framework that you'll carry with you throughout your entire career. Before we jump right into the clinical tools we use in clinic, let's just pause for a second. I want to test your baseline optical physics knowledge with a classic question. When we talk about magnification in ophthalmology, what's the actual difference between transverse and axial magnification? Take a second to think about that. How would you explain it? All right, let's dive into it. So while transverse magnification deals with heights or widths, like measuring the diameter of a choroidal nevus, axial magnification is totally different. It dictates how deep or elevated a structure appears along your visual axis. It's all about depth perception. Think about the elevation of that nevus pushing up into the vitreous. Now, mathematically, deriving this exactly is incredibly laborious, literally a nightmare. But for our purposes, we use this beautifully simple approximation. Axial magnification is just about the square of the transverse magnification. Quick look at our agenda for today. We'll be defining axial magnification, looking at the optics of direct ophthalmoscopy, navigating the Galilean telescope trap, checking out the mechanics of indirect ophthalmoscopy, calculating BIO axial magnification, and finishing up with some high-yield OCAP pearls. Section 1. Defining axial magnification, the physics of depth. Let's get right into it. Like I just mentioned, getting the exact axial magnification involves some really complex math. But for clinical life and honestly for testing purposes, you absolutely must remember this OCAP pearl. It is well approximated as the square of the transverse magnification. If you know the transverse mag, you literally just square it and boom, you're most of the way there. We're going to see exactly how this plays out in a realistic clinical scenario in just a bit. Moving on to Section 2. Optics of direct ophthalmoscopy, the 15 by magnifier. Now, what's wild about the direct ophthalmoscope is how incredibly simple the optical setup actually is. You're looking directly at the retina. Imagine you're holding the retina in your hand and just looking at it through a magnifying glass. The scope itself, it's basically just acting as a fancy flashlight. The resulting image you get is upright, it's virtual, and it is highly magnified. But here's the catch. The image is purely two-dimensional. Because you don't have stereopsis, direct ophthalmoscopy is a notoriously poor tool for appreciating things like subtle macular edema or really evaluating the cupping of the optic disc. So where does all this magnification actually come from? Well, it comes from the patient's own eye. Time for some active recall. Based on the Gilstrand reduced schematic eye, what is the assumed total power of the human eye for the boards? Yep, it's 60 diopters. Because you're looking through a 60 diopter lens, which is the patient's cornea and lens combined, the magnification is calculated by dividing 60 by 4. That gives you an impressive 15x magnification in a perfectly emmetropic patient. Which brings us to Section 3, the Galilean telescope trap, refractive errors. Okay, pay close attention because this is a classic board question and a super common point of confusion. Let's break down the why here. If your patient is a myope, their eye effectively acts as a plus error lens. To see it clearly, you have to dial a minus lens into your ophthalmoscope. So you're now looking through a minus lens, followed immediately by a plus lens. What optical instrument does that setup mimic? A Galilean telescope. And just like a telescope, the image of a myope's retina is going to be magnified compared to an emmetrope. On the flip side, if you're examining a hyperope, their eye is a minus error lens. So you dial in a plus lens on your scope. Plus followed by minus creates a reversed Galilean telescope, which means the image is actually minified. Do not confuse these two. It's a guaranteed trap. All right, Part 4. Mechanics of indirect ophthalmoscopy, prisms and aerial images. Let's switch gears to the BIO. Now this brilliantly illustrates why binocular indirect ophthalmoscopy, or BIO, is an absolute game changer for depth perception. Unlike the direct scope, your BIO headpiece isn't just a glorified light source. Inside that headset is a clever system of prisms and mirrors designed to physically reduce your effective interpupillary distance, your PD. It takes your standard, say, 60mm PD and shrinks it way down to about 15mm. Why on earth would we want to do that? So that both of your visual axes can physically fit inside the patient's tiny pupil. That is exactly what grants you binocularity, and crucially, true stereopsis. Because of this wild setup, the properties of the image change completely. You are no longer looking directly at the retina. The condensing lens you're holding gathers the light from the patient's eye and creates an aerial image floating in space right there between the lens and your eyes. That aerial image is what you're actually examining. It's a real image and, super importantly, it is reversed and inverted. Because it's reversed and inverted, you gotta remember, when you see pathology at the top of your lens, it's actually located inferiorly in the patient's eye. Take a really close look at this diagram. I want you to memorize this for the boards, because it literally explains the entire system. During BIO, there are three perfectly conjugate planes: the patient's retina, the aerial image floating in front of the lens, and your own retinas as the observer. Light from a specific point on the patient's retina focuses to a corresponding point on the aerial image, which then focuses perfectly onto a point on your retina. It's an unbroken chain. Section 5. Calculating bioaxial magnification step by step. Let's do some math. Let's look at a realistic clinical scenario. You're examining a patient and, whoops, you spot an elevated choroidal mass. Let's say the actual height of this mass, its physical elevation off the retina, is exactly 3 millimeters. What will be the perceived height of its image when you're looking at it with your standard 20-diopter condensing lens? Take a second. How would you even set up that calculation? Well, to answer this, we need to correctly calculate the axial magnification of our specific BIO setup. So, we're going to follow three highly structured steps to get our answer. Step 1. Find the transverse magnification. We do this by taking the ratio of the eye's power, that's U, to the lens power, that's V. Step 2, we square that transverse magnification to approximate the baseline axial magnification. And step 3, listen, this is the step literally everyone forgets. You must adjust for the interpupillary distance reduction by dividing by 4. Okay, let's walk through the math together. First, we use the 60-diopter standard for the patient's eye. We divide that by the power of our condensing lens, which here is 20 diopters. 60 divided by 20 gives us a transverse magnification of 3x. This simply means the image of the mass looks 3 times wider than it actually is. Next up, we have to deal with our depth perception. Remember how the BIO headpiece used those prisms to squeeze our baseline 60mm PD down to 15mm? Well, 60 divided by 15 is 4. Because our effective baseline for stereopsis was compressed by a factor of 4, our depth perception is mathematically reduced by a factor of 4. Now, listen closely to me. This is a massive board trap. Do not just square the transverse magnification and call it a day. You absolutely must account for this reduction. All right, let's bring the whole thing together. We take our transverse magnification of 3 and we square it. That gives us 9. Then we take that 9 and divide it by our PD reduction factor of 4. 9 divided by 4 yields a final BIO axial magnification of 2.25x. So, going all the way back to our clinical case, that 3 mm high choroidal mass, it's actually going to appear to be 6.75 millimeters high to you during the exam.
And finally, Section 6, High-Yield OK-PAP Pearls, Rapid Review. Let's lock this in.
Never ever forget the Galilean trap. When you use a direct ophthalmoscope, myopes magnify the image because the setup mimics a Galilean telescope. Hyperopes minify the image because it mimics a reverse Galilean telescope. If you can confidently explain the optics of why this happens using those plus and minus error lenses, you will literally never miss this question on test day. Second huge takeaway. If they ask you to calculate bioaxial magnification on a written board, I want you to immediately write down divide by 4 in big letters in the margins of your scratch paper. That way you won't fall for the distractor answer. The test makers know exactly what you'll do. They know you'll remember to square the transverse mag, and they will absolutely include that unmodified number as option A or B to trick you. Always divide by 4 to account for the PD reduction. I'm going to leave you with this clinical challenge to calculate on your own time. What happens to your axial magnification, your depth perception, if you switch from your standard 20-diopter lens to a higher power 30-diopter lens? Run the numbers through our 3-step formula. Mastering this intuitive relationship between lens power, field of view, and depth perception is going to ensure you are fully ready for both the wards and the OCAPs. Thanks for joining me on this explainer, everyone, and I'll see you next time.